In this episode of Remote Linear Algebra, we will be discussing how to find the eigenvalues of a matrix. The eigenvalue of a matrix is a constant such that if you take the matrix and you multiply by some special vectors, you get that constant multiple times the vector. If you remember how to multiply matrices, you go across the rows and down. So this equation where the matrix times some special vector ends up equaling a constant multiple times the vector creates the equation negative 6x plus 2y plus z equals lambda times x. Lambda is our constant. For some reason, the textbooks somewhere along the line chose the Greek letter lambda for these eigenvalue constants, but don't feel restricted to that. You can use whatever letter or variable you would like. Then the second equation will be 2 times x plus 2 times y plus 1 times z, and that should equal lambda y. And then the third equation will be 0 times x plus 0 times y plus 8 times z, and that should equal lambda z. So you get this system of equations. In order to solve the system, we need to collect like terms. So lambda x would need to be subtracted from both sides, lambda y would need to be subtracted from both sides, and lambda z would need to be subtracted from both sides. So that creates this system set all equal to 0. Notice the coefficient on x in the first equation is negative 6 minus lambda. The coefficient of y in the second equation is 2 minus lambda, and the coefficient of z in the third equation is 8 minus lambda. If the vector xyz is just 0, 0, 0, then we are automatically going to get a constant multiple of 0, 0, 0, because 0 times anything is 0. But we're not interested in that trivial solution. This is always true. Instead, we're interested in the non-trivial solutions. We want a solution to this system that's not trivial. So if there's a non-trivial solution, then the determinant of the system has to equal 0. Remember, if it equaled a non-zero number, that means that there's a unique solution, and that unique solution would have to be the trivial solution, 0, 0, 0. So we want any values that make this determinant specifically equal to 0. That equation is called the characteristic equation. If you remember how to do the cofactor process of determinants, that's what I have worked out here. So remember the matrix that we're actually finding the determinant of is the coefficient of x is negative 6 minus lambda, the coefficient of y, the coefficient of z in the first equation, and then the second equation, 2 is the coefficient of x, 2 minus lambda for y, 1 for z, and then the third equation, 0 for x, 0 for y, 8 minus lambda for z. So we're taking the determinant of that matrix and doing the cofactor process. So I go across the row, okay, so I'm going across this row, and so I take this times the determinant here, and then I subtract this constant times the determinant made with 2, 0, and 1, 8 minus lambda, and then I add 1 times the determinant made by these 4 values here. So we end up with this calculation, negative 6 minus lambda times the determinant of that 4 corners minus 2, and then you pick all of the items that were not in the same row and column as that 2, and then we add 1 times, and then again the determinant formed by all items that were not in the same row and column as that 1. And that will give us negative 6 minus lambda. I'm multiplying these two together, and then I subtract these two multiplied together. That's how you find the determinant of a 2 by 2. So these two get multiplied, and then I subtract 1 times 0. Then I have minus 2, and then I multiply this diagonal, 2 times 8 minus lambda, and then I subtract 1 times 0, and then I add 1, and I multiply this diagonal, 2 times 0, and I subtract 2 minus lambda times 0. So I get this calculation. Things clean up a little bit here. There's a lot of zeros, so if I distribute the negative 6 minus lambda through, I have these three factors multiplied together. This conveniently is a 0, so the minus 6 minus lambda times 0 goes away. Negative 2 times 2 is 4, so I have minus 4 times the factor 8 minus lambda. Again, negative 2 times the 0 creates a 0. And then this is 0 here, so the 1 times that factor goes away. And I have an 8 minus lambda in both of these terms, so I can factor that out. And when I do factor that out, I get 8 minus lambda as a factor, and then I get lambda squared plus 4 lambda minus 16. So that is, if you multiply these together minus 4, again, factor out 8 minus lambda, and you'll get this left after you clean it up. If you then multiply the 8 minus lambda through here, you get negative lambda cubed plus 4 times lambda squared plus 48 times lambda minus 128. So you can represent the equation in this polynomial form, or if you want, you can represent it in its factored form. We're actually interested in the zeros because the zeros, or the solutions of the equation, are our eigenvalues. We can easily see that 8 is one of the zeros, and then if you do quadratic formula on that other factor, we didn't get nice rational numbers. Instead, we got the irrational numbers, negative 2 plus 2 times the square root of 5, and negative 2 minus 2 times the square root of 5. So those are the three eigenvalues of that matrix. And the polynomial is the characteristic equation. I guess we should actually have it set equal to 0 to actually make it an equation. So we'll put 0 over here. Okay, so the characteristic equation is this polynomial set equal to 0. And we call that the characteristic equation of our matrix. And that's how you find the eigenvalues. You consider this idea that you want this multiplication to equal a constant multiple of the vector you started with. You create a system set equal to 0, and then the determinant of that system has to equal 0. Otherwise, you just have the unique solution and the matrix actually doesn't have any eigenvalues. If it has eigenvalues, it means that this determinant needs to have some real zeros. Again, they don't have to be nice, clean numbers. They can be messy numbers, but they need to be real numbers, not complex numbers. And if you then work out that determinant using cofactors or whatever method you would like, you end up with a polynomial, and that polynomial set equal to 0 is the characteristic equation of the matrix. The zeros of it are the eigenvalues.